Hi, everyone. So I think we'll get started. So I still haven't taken a look on your exam because I would like your papers to sit maybe for a day or two before I actually grade on your exam. Okay. So I might be able to grade them before tomorrow's lecture. Okay, or might be not, but we'll see. Okay, I will let you guys know tomorrow. So we'll be looking at the reminder of chapter 4 here, but before we get started, let me just give you a reminder. So or the announcement, because homework 4 is up online. This is the first time that's been mentioned, so it's online now. And then it's due on Tuesday next week. Okay, so you have about 1 week. Just give you a heads up that next homework is probably going to be due like 1 day earlier than usual, because we kind of lost a few days due to the exam one. So I would like to keep make up some pace on the homework assignment, because usually it's given like once per week. So for the next homework, it's probably going to be due on Monday, the week after the fourth homework will be due. Okay. And then the next one will be like about 1 day earlier than the one before it. Okay. So let's check the last two sections of chapter 4 today. So earlier sections, we talk about two-dimensional motion, and then we talk about the projectile motion, which it's a particular two-dimensional motion. So today we are going to check on another special two-dimensional motion, that is the uniform circular motion. Okay, so when an object is moving with uniform speed or the same speed in a cycle, so then it's called uniform circular motion. So the speed remains the same, but it's a circular motion. So in that case, the velocity actually is changing all the time, because velocity has the magnitude, which we call speed, and also has direction. So in that case, you can see for uniform circular motion, the direction of velocity changes all the time. Okay, you can see this vt on the graph here. At the instant time t, it's pointing in this direction. Now in the later time instant of t plus delta t, then it's pointing in this different direction. Okay, so you can see the direction changes all the time. Although its length doesn't change, okay, that means speed doesn't change, but direction changes all the time. So then velocity is changing all the time. Okay. So in that case, then this uniform circular motion for the object, it actually will have an oscillation, because the velocity is changing, or the direction of the velocity changing. So then velocity is changing. Okay, so then it will have an oscillation. Okay, but the oscillation here does not change in the magnitude of it. It only changes the direction. Okay. So if we look at the velocity vectors in the green at two time instants t and delta t, and then if we look at the position vector at t and then time t plus delta t in the purple here, so you can see from t to t plus delta t here, the position has a change in the form of vector delta r, which is r t plus delta t minus r of t. Okay, so then that's its position change or displacement. If you look at the two velocity vector here, now let's move them out of the circle here to on the side here, right hand side here, this small triangle over here. You can see on the right here, this is v of t instance. Okay, and then pointing to the left, this vector is the v t plus delta t. So you can see also this two vectors, the change of velocity is indicated by this black delta v vector. Okay, so this is change in velocity. Okay, we kind of move the v vectors parallelly over here. Okay, so because the velocity in this case, okay, for a uniform circular motion, it actually is perpendicular to the position vector. So for r of t and then v of t. So these two are perpendicular to each other. For r of t plus delta t and then v of t plus delta t, these two are perpendicular to each other, okay? So then in that sense, v of t and then v of t plus delta t will have the same angle. These two vectors will make the same angle as r of t and then r of t plus delta t, okay? And then because r of t and then r of t delta t, this has the same length, but just pointing at different directions because this is a uniform circular motion. So then it's radius, both r vector are the radius, okay? So then those have the same length, and then this v and v plus delta t has the same length. So then the larger triangle on the left here formed by r of t delta r and then r of t plus delta t, and then the small triangle here on the right here formed by v of t delta v and then v of t plus delta t. They are actually similar angles, similar triangles, okay? So these two are similar triangles. So because of the fact that these two triangles are similar triangles, you can come with the relation of, so magnitude of delta V over V should be equal to delta R over R. Okay, so we can write that relationship. So before I move to the next slide, I think I forgot to mention the oscillation for a circular, uniform circular motion, because of the factor that it actually changes just the direction of the velocity, and then it actually pointing towards the center of the circle. So then that oscillation is always called, it's also called centripetal oscillation because it's pointing towards the center of the circle. Okay, so that's the name of the centripetal oscillation over here. All right. And then let's then take a look on the relationship we just came up on the size of the two similar triangles. Okay, so let's go to next slide. So as I mentioned, you can write delta V, just the magnitude without an arrow, over V equals to delta R over R. Okay, so from the two similar triangles, and as the definition of oscillation is being defined as delta V over delta T, so you can take a look on this guy here. So on the first equation here, on the top on the slide here, you can divide both sides by delta T. Okay. And then let me show you on the paper here. Maybe easier to show you the algebras on the paper. All right. So from the triangle, we can write delta V, just the magnitude over V equals to delta R over R, right? Now, if we divide both sides by delta T, so then delta T on both sides, right? That also it's valid there, okay? Then if we divide both sides now by V, so that means multiply both sides by V, actually, I'm sorry. V times that, and then times V on this side, okay? So then you get rid of V here. So then you can see this is delta V over delta T, which is A, right? Oscillation equals to delta V over delta T, right? And then this is equal to delta R over delta T. Okay, delta R over delta T times V over R. Okay. Now, if you remember, when we get the velocity from definition, it should be equal to delta R over delta T, right? So then this guy will give you velocity V. So then this is equal to V times V over R. Okay, and then this is equal to A. So oscillation then is equal to V times V over R. Okay, so then you have two V's, so then it's V squared over R. Okay, so this is your oscillation. So from here you can see oscillation of uniform circular motion or centripetal oscillation that's equal to V squared over R. Okay, so this is the magnitude for the oscillation for a uniform circular motion. All right, and then the direction, as we mentioned earlier, it's always going to be pointing towards the center of the circle. Okay, so it's changing all the time, but that's the direction. The magnitude doesn't change. It's v squared over r because v and r are not changing. Okay. All right. Now for a uniform circular motion, you can sketch the motion like this. Okay, so if you set up a x and y coordinate system like this, all right, so then if you trace the position of your object, it's going to be on the circular track. Okay, at any time instance t, so r of t. Okay, so then you can actually express this guy as the angle as, okay, because this is uniform circular motion, so the change of in angle should be also um, constant over the time. So that means at the same time delta t, it will change by the same angle delta theta. Okay, so so when you do that, now the angle changes over time t. All right, if we call that angular speed because that's changing in angle, right? So we can call it angular speed or angular velocity, or sometimes referring to angular frequency. So you can see if the time it takes for an object to go one full revolution, if we call that as period, because then a period means the cycle, the time it takes for an object to repeat its motion, right? So then t is the period of the motion. So then for one revolution, the change in angle will be in 2 pi, okay, in radians, or 360 in degrees. So then the angular speed or angular velocity here should be equal to 2 pi over t, okay? So typically when we talk about angular speed or angular velocity, we take the counterclockwise as the positive direction, right? And then clockwise to be a negative direction, okay? Just keep that in mind. But again, as it could be arbitrary, but the conventional way is take counterclockwise to be the positive direction. Okay, so if we do that, then our velocity, okay, so in this case you can see, so the velocity, the magnitude of the velocity v, okay, then it's going to be equal to r times omega, okay, because for omega is equal to 2 pi over t, but for velocity, it's going to be equal to the distance traveled over time t. If we take t as one period, then for one period of time, the distance traveled should be the circumference of the circle. So it's 2 pi times r, okay, over t. So this guy is omega, right? It looks like W, but it's called omega. So then V, so you can see that V is equal to omega times R, okay? So if you express the angle as, or the speed as angular speed here or angular velocity here, then there's a relationship of V equals to R times omega or omega times R, either way, all right? So if you are given angular velocity or angular frequency here, then centripetal oscillation can be rewritten in terms of the radius and the angular velocity. Okay, so you just replace the v in the first equation here with omega r. So then this becomes omega r square over r. So this is omega square r square over r. Okay, so one r here will cancel out the square on the top there. So then it gives you omega square times r, or r times omega square. Okay, so then centripetal oscillation can be written as r times omega square. Okay, so either this way or that way, right? So these are the two expressions for centripetal oscillation. All right. So the radius here, or the magnitude of the position vector here, it's also called the magnitude of the position vector, okay? Because this guy is always going to be the fixed number. For example, if it's 1 meter, then it's always going to be 1 meter, okay? So it's called the amplitude of the position vector, okay? And this position vector, you can resolve it into x component and y component. Okay, so just take the magnitude. That means take absolute value. Okay, so when you see the absolute value, that is applied, or the signs of absolute value applied to a vector, that means you are taking the magnitude of it. Okay, I think it looks like this is the first time that this sign appears on the vector. So yeah, so it's the magnitude of it. Okay, so magnitude of times cosine of the angle here, that gives you the x component, and then magnitude times sine of the angle, omega times t will be the angle, because if you take this as the 0, then omega times t will be how much angle it forms with this positive x. Okay, so then that will be the y component. This x component, that's y component. Okay, so the position vector then can be written as a times cosine the amplitude times cosine of the angle times I times plus 8 sine omega t times the j direction, so the y component. Okay, so you can see the components are function of as a function of time t. Okay, they change as cosine as the x component, and then sine as the y component. All right. So this is for uniform circular motion. You can express the position vectors in this format. Okay, the x component and y component. And you can do, because you now know the position vector in x component and y component, this is two-dimensional in the ing form, then you can get your velocity vector, right? Because velocity vector is time derivative of the position vector. Okay, so position vector has two components, then velocity vector will also have two components. When you do derivative of a cosine omega t, okay, so then cosine becomes negative sine, right? So there's a negative sign. A remains because it's constant. Okay, a of sine here. Now, as I mentioned, I think a couple of weeks ago, when you do cosine, derivative of cosine, if this is there's a parameter, constant parameter before your variable, then you will take that parameter outside as well. Okay, so a times omega. So you are again doing derivative of omega t over t times derivative of omega t. That gives you omega. So this is where this omega is from. So it's minus a omega sine of omega t plus, similarly here, when you do time derivative of sine, gives you cosine. Okay, but there's omega inside the parenthesis, then it comes out as well. So a omega cosine, okay, in the j component. So this is the vector, the velocity vector forming I and j. Now, for the acceleration, then you take time derivative of your velocity. Okay, so that means doing time derivative of this x component and y component. So sine becomes cosine. All right, now omega, you will have one more omega coming out, so it will be minus a omega square. All right, and then time derivative of cosine becomes sine with a negative sign, so minus a omega square sine omega t. Okay, so this is your acceleration vector for uniform circular motion. Okay, so these three equations will give you the equation of motion for a uniform circular motion. Okay, to find its position, velocity, and acceleration. All right. Okay, so let's take a look on an exercise problem here. Okay, so it says a point located on the second hand of a large clock has a radical oscillation of 0.1 or radial oscillation of 0.1 centimeter per second square. How far is the point from the axis of rotation of the second hand? Okay, so it tells us the acceleration of it. All right. Although we just look at the ij component, but I don't think this one is related to the ij component. Okay, you can just use the magnitude of the acceleration. Okay, so this acceleration is in the radial direction. That means the centripetal acceleration. Okay, so that gives you the centripetal acceleration. And then it's asking you what would be, how far is the point from the axis of rotation of the second hand. So this is like, what would be the radius of this point, okay? So you are given oscillation, you are looking for radius, right? And then you'll be looking at like oscillation in this form or in that form, okay? So you probably can figure out, because you are given centripetal oscillation, you are looking for R. So you'll either have to know the speed of it or the angular speed of it, okay? So think about if you can figure out either speed or angular velocity, okay? And then you should be able to solve for that. And if you have your answer, you can click on the problem here to submit your answer, okay? All right, looks like a couple of you guys have submitted your answers. I'll wait for another 30 seconds, then we can take a look on the solutions together, okay? All right, so we know for centripetal oscillation is going to be either R square V square over R or R times omega square, okay? So we are given centripetal oscillation, we're looking for the radius R. Now, we probably couldn't figure out velocity here or the speed here because we are not given R. So we wouldn't know the distance travel over time t, right? So probably we're not going to do it that way. We can try to see if we can figure out this angular speed here. So for angular speed, if it tells us this is a second arm, so that means for every 60 seconds, right? It the angle that is swept is like 2 pi for the angle in radius, right? So this is theta, this is time t. So if you do theta over time t, that will give you angular, or delta theta over t, that will give you angular speed, okay? So we can kind of figure this out, okay? So let's do this, use this guy here. So we'll be figuring out our angular velocity or omega here. So by doing 2 pi divided by 60 seconds, okay? So then this would be equal to, or actually I didn't do it. I just derived the equation from here. So from here, it tells me that R is going to be equal to centripetal oscillation over omega square, okay? So it gives me that my centripetal oscillation is 0.1 centimeters per second square. So divided by 2 pi over 60 seconds squared, okay? So if you plug everything into your calculator, this is going to tell you it's going to be 9.1 centimeter, all right? Now, that's your final answer, or if you want to keep the just one sig figure, it's 9 centimeter because the problem gives you one sig figure as the known, so you can do it that way, okay? All right, so as I mentioned, just to emphasize this again, so expert PA probably doesn't care about sig fig. So if you submit 9, if it says it's wrong, then you probably want to submit 9.1, okay? Because it has the tolerance of maybe plus or minus 5%, okay? So point one looks like it's about 10 or 11% of the answer, okay? So that in expert TA, you may just forget about the sig fig there, all right? The responses I see here is 9 centimeter and 9.1 centimeter. So you guys were right. Okay. All right. Any questions you guys might have? Just unmute yourself and speak up. Okay. Also, I want you guys to know that since for the lecturing part, maybe the pace might be a little bit faster, but at any point, if you have questions or doubts, just stop me. Just say, I have a question. Okay, so then I can stop and answering your question. All right. All right. So let's keep moving on here. Over here. All right. Okay, so we talk about uniform circular motion. So what happens to a non-uniform circular motion? So in a non-uniform circular motion, so the speed changes. Okay, so that means speed changes, but now you are still a circular motion. So the speed is changing, and then the direction of the velocity is also changing all the time, okay? Because it's on a track of circular track. So then at any time instance, the direction of the velocity is different, all right? So then you'll have two oscillations here. So one oscillation is changing the direction, or we should say two components of this oscillation. One component is changing its direction, and then the other component is changing its speed, okay? So the component that is pointing towards the center, again, it's the centripetal oscillation, okay? And then the other component will be perpendicular to this guy in the tangential direction. So that's the, that changes the speed, okay? So then these two are perpendicular to each other. So then the overall or the total oscillation should be combination of centripetal oscillation and tangential oscillation, okay? So it will be a vector summation of the two because the oscillation is a vector form, okay? So the total will be pointing somewhere in this direction, okay? It's a combination of A centripetal and then A tangential, okay, are in this equation over here, okay? All right, so that's section 4.4 circular motion. So one uniform circular motion, and then another topic on the other topic on non-uniform circular motion. Let's check on the last section of this chapter on relative motion in 1 and 2 dimensions. Okay, so we'll focus on the 2-dimensional here. First, let's look at what's called frame reference frame. Okay, so when we were doing like the either 1-dimensional or 2-dimensional or general like 3-dimensional motion, we say we should set up a coordinate system. Okay, so that's our frame of reference. Okay, where that you will define your origin, and then you will use the origin and then to define your relative positions, etc. Okay, so those are called frames, reference frames. Okay, so typically in most examples we would have examples so far, the frames of reference would have been the Earth. Okay, so we set Earth as our frames of reference, and then we kind of choose origin, our origin arbitrary. Okay, but Earth is a good reference of reference because every object that we'll be talking about so far, it's compared to the Earth is small, okay, and then we are moving along with the Earth, okay, so it's kind of relative stationary there. Okay, but sometimes it might be convenient, or maybe turns out to be more feasible to choose another frame of reference. For example, when you are walking inside a train, okay, so you probably will notice it's easier to measure your speed with relative to the train. So that's called relative motion, okay? And then the train is also having relative motion with the earth or the ground. So in this case, if the train is just going in one direction with 15 meters per second, so then you can write this velocity as velocity of the train with respect to ground. So v tg, okay? So that's the velocity of the train with respect to the ground by using subscripts. You can then write your velocity as a vector of v of person with respect to the train. Okay, so v of p relative to t. Okay, so it might be easier to measure your velocity relative to the train, and then the train's velocity with respect to the ground. But what's your velocity with respect to the ground? The velocity of v p g. So means passenger or person with respect to ground. So if you have the V of PT and then V of TG, then you can actually add the two up to get your V of PG, okay? So the rule is here, if you have this, the second subscript matches up with the, of the first one, matches up with the first subscript of the second vector. When they add up, then this subscript will disappear. Okay, the resultant will be V of PG, okay? V of P relative to G. I think we kind of mentioned this earlier when we talk about vectors, okay? But we will take a look on some detailed examples here, okay? So this is what happens when you have one-dimensional motion, okay? This equation also applies to two-dimensional motion, relative velocities for two-dimensional motion. So say if the train is going in the horizontal way, but if you are climbing up with the train with certain velocity, okay, so then you can also use this vector addition with vectors expressed in subscripts, okay, as long as the second subscript on the first vector matches up with the first subscript on the second vector, then this subscript will cancel out, okay? So then V of person with respect to the ground will be equal to V of person with respect to the train plus V of the train with respect to the ground, okay? So then you can use this equation. And then graphically way, this is what you have, okay? So this is what you have in graphically way, all right? That describe this vector addition graphically over here, okay? Now you can also use numbers as your subscripts, okay? Then will be the same. As long as the second subscript matches on the first vector matches the first subscript on the second vector, then that subscript will disappear, okay? So then you'll get this result. And then if you have to flip the two subscripts, then V, for example, V of BA should be equal to minus of V of AB. Okay, so then it becomes the inverse of the original vector. Okay. All right. So at the end, let's take a look on one example here. On this one, I think I'm going to set up breakout rooms for you guys so you guys can discuss how you want to solve for this and then probably solve for the problem with each other inside this your breakout room, okay? So let me stop sharing, but open up breakout rooms. Let's say maybe 3 rooms. Okay, I'm going to just randomly assign the breakout rooms. Okay, so then I'll give you guys about probably say 5 to 8 minutes, and then we'll come back to the main room to check on the solution together. Okay. You will have to click on join in the breakout room to join the breakout rooms. Okay. All right. So I think you guys are all back. So we can take a look at the solution together. So first we can set up an X and Y coordinate system. Okay, so X to be horizontal, Y to be vertical, or horizontal to the right to be the east direction, and then normal direction or north direction to be the upward positive direction. Okay, so it says a passenger walks from one side of a ferry to the other as it approaches a dock. If the passenger's velocity is 1.50 meters due north relative to the ferry. So then this is the passenger velocity relative to the ferry. Okay, so you can sketch it this way. Let me see. Do I have a red pen somewhere? All right, found one here. So over here, okay. So V of the person with respect to the ferry. So V PF, okay. And it says, so this is due north, so it's just going up north, okay. So, and it says 4.5 meters at an angle of 30 west of north, relative to the water. So 30-degree west, this is west of north, so then in that direction, okay, somewhere in that direction, 4.5, about 3 times of that one. I'm probably not going to have the right scale about that way. So this is a person with respect to the water. So PW, VPW, okay? It's asking you what are the direction and magnitude of the ferry's velocity relative to the water. So you are looking for V of ferry to water, relative to water, okay? So that's what you are looking for. Now let's take a look. If you want to find this guy, then we can actually come up with this relative velocity, right, in this subscript form. So you can do, because there are 3 objects here mentioned, the passenger, water, and the ferry. So you can do velocity of ferry to the passenger plus velocity of the passenger to the water, right? To get you the velocity of ferry to the water, okay? So this is how you want to come up with the plane here. Now it gives us P of V of PF, but we need V of FP, right? So you are switching the 2 subscripts. So that means it becomes negative of original PF, right? And then plus the VPW. So VPW is given, this guy is given, so then you can kind of solve for your V of FW, right? But remember, this is in the vector form. You don't just add them up, okay? You don't just do like minus 1.5 plus 4.5, but you want to do components way here, okay? So, or if you want, you can do the triangle method, okay? So either way. For the component way, so this is going to be, so you are going to figure out what's the X component of this guy and then Y component of it, okay? So it looks like this guy is in the Y direction, so the X component of it is 0, okay? And then the Y component of it will be just 1.5 meters per second, okay? Now on this guy here, the X component will be the 4.5 meters, right? And then this is 30 degree. So then it's going to be this part, okay? So if this is 30 here, you can use the 30, or you can use directional angle of 120. If you take this as 120, then it will be easy to just use 4.5 meters per second times cosine of the directional angle of 120, okay? Then you don't have to worry about, if you use 30 here, you will have to do like the 4.5 sine of 30, and then but with negative sign, because this is pointing towards the negative, okay? So the Y component then will be 4.5 meters per second, but sine of its directional angle, okay? So then we can do the X component here. So V of vary with water, the x component should be equal to minus of 0 plus the x component, this guy, 4.5 meters per second times cosine of 120 degrees, okay? So that would be minus 2.25 meters per second. That's x component. Then its y component, it will be negative of 1.5 meters per second plus 4.5 meters per second sine of 120 degrees, okay? That will give you let me see. Yeah, looks like my original algebra doesn't look right there. All right, so yeah, you guys can do this, or let me just double check with this. So minus 1.5 plus 4.5 sine of 120 degrees. So it gives me 2.397 meters per second. Okay, so this is my y component, right? So now I have my x component and y component, so I can do this component method, the x square plus the y component square. Okay, so minus 2.25 square plus 2.397 meters per second square, and then square root. Okay, so again, I think my original number was wrong, so I probably didn't have a right number, but let me just double quickly check on this. 2.397 square. Okay, so I get about 3.287 meters per second, or 3.29 meters per second. Okay, so that's my magnitude. My directional angle, I can do the theta of Fw, which it will be tangent inverse of the y over the x. Okay, so tangent inverse of 2.397 over minus 2.25. Okay, that will give me a tangent of 2.397 divided by minus 2.25 degrees. So it looks like minus 46.8 degrees, or 81 degrees. All right. Now again, as I mentioned, because this x component is negative, right? It's negative for the x component, so you want to add 180 degree to it. Okay. So 180 plus negative 46.81, that will be 133.19 degrees, okay, or roughly 133 degrees, okay. So for the directional angle on this guy, let me see if I can capture the whole picture here for you guys. All right. All right. Any questions you guys might have? Okay, so if not, then I think we just finished chapter 4, and then we'll stop here for today. Okay, I'll see you guys tomorrow. Bye, guys.